In this video, we're going to look at definite integrals. So what have we learnt so far? Well, we have found general expressions for the area under a curve or function. However, this doesn't actually get us a numeric value for the area between specific limits, such as x equals 1 and x equals 3. For this integration process to be useful, we need to find a way to get specific areas under a curve. In this slide, you can see a generic curve with an area painted red beneath it, between the limits of x equals a and x equals b. These are the type of areas that we want to be able to find. This is where the fundamental theorem of calculus comes in. This theorem provides a link between the concepts of taking an integral, or anti-differentiation, and the problem of finding areas under curves. This theorem provides a way to use our integration skills that we have previously learned to find the area under a function between two x values, such as x equals a and b in the previous slide. In this course, we will not go through the proof of the theorem, as it is a bit too complex. However, we can use the result, which is far more important and helpful. So, the result of the theorem is that if we want to find an area under a curve, let's call it f of x, between the limits of x equals a and x equals b, as shown in the previous slide, and the integral function, or the antiderivative of f of x, is g of x, then the area is equal to the integral function of f of x, that is, g of x, evaluated at x equals b, minus g of x evaluated at x equals a. This means that we're taking the difference between the integral function evaluated at one limit and the integral function evaluated at the other limit. Let's look at an example which will make it clear. In this example, we want to find the area under the curve y equals x squared between the limits of x equals 1 and x equals 2. So, let's let f of x equal x squared. Therefore, the integral function, or the antiderivative, g of x, is equal to x cubed on 3. Now, from the fundamental theorem of calculus, the area is equal to the integral from 1 to 2 of x squared dx. Now, when two numbers are put on the end of the integral sign, in this case the 1 and the 2, that just means that we're taking the definite integral, or the area under that curve, between those two values. So in this case, it's between x equals 1 and x equals 2. Now, from the theorem, this area is equal to our antiderivative function, or the integral function, which is g of x evaluated at 2, minus that integral function, g of x, evaluated at 1, or g of 2 minus g of 1. So, when we put x equals 2 into x cubed on 3, we get 2 cubed on 3, and when we put x equals 1 into g, we get 1 cubed over 3. Now we take the difference between these two values, and we get 7/3. This is the area under the curve y equals x squared between the limits of x equals 1 and x equals 2. When evaluating a definite integral, we use a notation shown in blue here, where we put the integral function in large brackets, and we put the limits of integration, in this case x equals 1 and x equals 2, on the right hand side. After this lecture, please view the example video to see live examples of definite integrals being solved, and then have a go at the practice problems on definite integrals in our practice problem sheet. Then compare your solutions to the worked solutions. Thank you.